Welcome back to Probability and Statistics. This is our third lesson. We'll be looking at Chapter 5 in this lesson from the book Elementary Statistics, 4th edition by William Navidi. In this lesson, we're going to veer a little bit from what we've been doing in the past lessons. If you've been following along, we've been looking at data. We've looked at the types of data, or how we categorize data, how to collect data, display data in various visual representations. In the last lesson, we looked at how to describe data using things like shape, center, and spread. And so this lesson is going to veer a little bit from that as we start to look now at probability. Probability is a really important aspect or element of statistics, and we see it pop up in a number of different ways, especially in an introductory course like this. We'll see this in this lesson in what I would consider kind of a more traditional way of thinking of probability. We'll look at how to find probability using that idea of number of desired outcomes over total possible outcomes to find the probability. But as we progress through the lessons, we'll see probability show up in other ways that sometimes aren't even so obvious that we're actually finding probability. And so we'll see that in future lessons as we go. But like I said, this is kind of a little bit more of a traditional view of probability. We're going to look at what are the basic concepts. So we'll actually start by defining probability, especially from a statistical standpoint. We'll look at some other ways then to find probability given certain circumstances. So what do you do when you have, two different things that you want as a possible event, or you want this or that, or this and that, things like that. So we'll look at the addition rule. We'll look at the multiplication rule. We'll look at conditional probability, finding the probability of something happening given or conditioned on something else happening first. And then we'll finish up by looking at some counting methods, specifically the idea of permutations and combinations. How do we count the number of ways that something can happen? Because certainly we need to know that or be able to do that a lot of times to find a probability. All right, so with that, let's go ahead and get going here. So like I said, we're going to start with just some basics here. So just some definitions to help kind of put us all on the same page and just to be using common language as we progress through not just this lesson, but future lessons as well. So when we talk about probability, we want to start actually by talking about a probability experiment. A probability experiment is just a situation where we don't know any individual outcome. So a situation where we don't know any individual outcome. But we know the outcome over many repetitions. All right, so what does all that mean? Outcome over many repetitions. I always try to talk while I'm finishing, and that never works well. Okay, so what this means really is just this. So let's take, for example, a real simple example of flipping a coin. If I flip a coin, I don't know if that next flip is going to be a head or a tail. But what I do know is that if I flip that coin over many, many, many times, that I would expect to get about an equal number of heads and tails. So when we talk about a probability experiment, that's what we're talking about. That situation where I don't know what the next outcome is going to be, but I know that if I were to do the same thing over and over and over again, I could predict or tell what the results should look like. Rolling a 6-sided die, I don't know if the next roll is going to be a 1, 2, 3, 4, 5, or 6. But again, if I were to roll that die hundreds of times, I would expect to get all 6 numbers roughly an equal number of times. And if I do it enough times, I would expect to get almost the same number of 1s, 2s, 3s, 4s, 5s, and 6s. So that kind of brings us then to the definition of probability. And we'll define it this way. We'll say that the probability of an event, is the proportion, just think fraction, decimal, percent, is the proportion of times the event occurs in the long run. So sometimes when we think about probability, we might think about it more mathematically. We might think of it in terms of a formula, something like the number of desired outcomes divided by the number of possible outcomes. And that is certainly a way to find probability, and that would be what we call empirical probability, or a mathematically based probability. But really, in the truest sense, if we kind of broaden our thinking about what probability is, it's really just saying, if I were, again, this idea of doing something over and over and over again, if I did something many, many times, what would the proportion of times that the desired event would occur? So again, probability of flipping a head is 50%, probability of flipping a tail is 50%, because if I do it enough times, I would expect to get about an equal number of heads and tails. So both of these definitions, when we talk about probability experiment, we talk about over many repetitions. When we talk about probability itself, we're talking about kind of in the long run. Just that idea that you have to do something, though, many, many, many times before you can start to have that assurance that you're hitting on the right probability. I might flip a coin 30 times, and 20 of those times I might get heads. That is very possible. And I would come to a wrong conclusion if I believed then that there was a 66.6% chance, or about a two-thirds chance of getting heads on a coin. I would have to keep going and do it more and more and more before that probability, that proportion, would start to settle in at about 0.5. Okay, a couple more definitions here. Let's talk about law of large numbers, which is really what we've been talking about in these last two definitions. So law of large numbers just says that the proportion of times a given event occurs, so the number of times a given event occurs, will approach its probability as the experiment is repeated over and over again. So the probability as the experiment is repeated over and over again. So again, there's that idea of repetition, of doing something many, many times. And so, again, kind of like I was saying with the coin, so if you think about, if I were to graph, for example, the probability of getting heads, so this is maybe like number of flips, and our vertical axis might be a proportion of heads. So I might flip a head, and if this is 1 and this is 0, and here's 0.5, right, I'm going to put a little dotted line there. So I might flip a head, I might get a head, and so I'm at 100%. And then I flip it again, and I might get another head, and I'm still at 100%. And then I flip it again, and this time I get a tail, so I'm at 1/3, or about 33%, right? And so as we do this over and over again, this is going to fluctuate, right? This is going to go all over the place. But eventually, as we do this more and more and more, that probability, I'll kind of extend this out, the probability starts to settle in at its true probability, in this case of 50%. So that's just the idea of law of large numbers. Again, just the idea that we've been talking about over and over and over again in the last few minutes of repetition. All right, so that brings us now to sample space. So when we talk about a sample space, we are talking about the set of all possible outcomes. So the set of all possible outcomes of a probability experiment. So again, when I think about some kind of a situation, flipping a coin, rolling a die, doing both, whatever the case may be, a sample space is just a list of every outcome that's possible. So for example, if I flip a coin and I roll a 6-sided die, so I'm looking at the result of the coin combined with the result of the die, and I want to know the sample space, well, I could get a head on the die and a 1 on the, or excuse me, a head on the coin and a 1 on the die. I could get a head and a 2, head 3, and so on and so forth. Kind of get the idea here. And then the same thing could happen with the tails, right? I could get a tail with a 1, 2, and so on and so forth. So my sample space in this case has 12 elements, just every possible outcome of rolling or flipping a coin and rolling a die. Which then takes us into the idea of a probability model. And a probability model is nothing more than a sample space, so what we just created, so it's a sample space, but we attach the associated probability with each event. So it's a sample space with a probability for each event. So using the example that we just did, I might do H1, H2, H3, so on and so forth, up to tail 6. And in this case, because each of them have an equal chance of happening, and there's 12 different outcomes, each would have a 1 in 12 probability. Now, obviously, not every probability model would look like this. You may have a probability model where the probabilities are different, things like that. You can make a probability model for example, of number of children in a family. And so you would have a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. 0 might have a 0.2 probability. One child might have a 0.3 probability. 2 children might have a 0.45 probability. So you could have different probabilities, obviously, depending on the situation. And to that example, they don't always have to be kind of the traditional flipping a die, or flipping a coin, rolling a die, drawing a card. Some of the things that we often use as examples when we talk about and learn how to find probabilities. Okay, so with that, let's go ahead and keep flipping coins and rolling dice, and we're going to look at then the probabilities of each of these events occurring. Now, one of the nice things about a probability model is that once you've made that probability model, you can then very quickly and easily figure out a variety of probabilities by just pulling the individual probabilities out of that model. Now, I wouldn't necessarily make a model by hand for a very, very large set of events. If I had a situation where there were, let's say, 200 possible outcomes, I don't necessarily want to make a chart for that. But think technology, So if you think about technology and how you would basically do the same thing using technology, where you could input then what is the event that you're looking for, and basically you could either create a database with the probabilities, where in this case you would just have it search for that combination, or more likely you would just use an algorithm then that would find the probability based on using mathematical formulas and things like that. Okay, so in this case, if I want to find the probability of heads and of 5, well, if I had made the entire probability model, showed every possible outcome, we would have seen that there was only one way to get a head and a 5, and there are 12 possible outcomes. So like all of the events in this probability model, there's a 1 in 12 chance, or 1 in 12 probability. Probability of tails, well, again, if we were to look at how many times tails would show up in this probability model, there would be 6 of them. So we would have 6 over 12 because we just add all of them together, or reducing that to, not 1 out of 12, how about 1 out of 2? Okay. Probability of heads or 5. So just be a little bit careful here. If we think about counting these out, and again, if I had written out all of the outcomes in the probability model, it'd be a little bit easier. I suppose I can go up to our sample space. I forgot I had that up there. So when I look at how many times I can get a head or a 5, there's 6 different ways of getting a head, or means, right, so head or a 5, so heads, doesn't matter what number it is, or a 5. Now in this case, we just need to be careful because there's 2 ways of getting a 5, but we don't want to double count the head and the 5. I just counted the head and the 5 with the heads, so really there's 7 ways, right? There's the 6 ways of getting a head, plus the tails 5 combination, so that would give me a probability of 7 out of 12. And then, tails in a 7. Well, obviously you can't roll a 7 on a 6-sided die, at least not a traditional one. And so in this case, it would just be 0 because it's not possible. All right, let's flip some coins, just exclusively here. So we're going to flip a coin 3 times. So again, define the sample space. I encourage you, as we go through this, just to kind of test your understanding, I encourage you to pause the video at any time and just try some of these examples on your own, and then go ahead and just skip ahead to the answer or watch to see the solution played out. So if you flip a coin 3 times and we're looking for the sample space, I try to be a little bit methodical when I'm doing this so I don't miss any. So for example, I'm going to start with 3 heads, and then I'm going to look at all the combinations of 2 heads and 1 tail. So I could get a head, head, tail. I could get a head, tail, head, or a tail, head, head. And then let's look at 1 head and 2 tails. So head, tail, 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 head, tail, and a tail, tail, head. And then 3 tails would be my last combination. So there are 8 elements or 8 possible outcomes in our sample space. And so the probability of 3 heads or 3 tails, well, of course, there's only one way to get each of those. We've got 3 heads, we have 3 tails. And so we have 2 out of the 8, or 1/4. If you want to simplify that down, reduce that down. C, what is the probability of flipping 2 heads given that the first flip was heads? So we have to be a little bit careful here. There's this idea of this given, and later we're going to define this as a condition, right? So I want 2 heads, but only under the condition that the first was also a head. So if you look at your possible combinations here, that's 1, and that's 1, and there are no others. So again, we've got a 2 out of 8, or a 1 out of 4 if we reduce that down. Okay. So let's talk about some, kind of move on to some other ideas here. Well, let's talk about unusual events. And so an event whose probability is small. So an event whose probability is small is considered an unusual event. So we define unusual event just simply as that, an event whose probability is small. Now, what is small? Is that 10%, 1%? Does it have to be like 0.1%? And so in this case, when we think about an unusual event, the rule of thumb that we're going to use in statistics is 5%. So if you have a probability less than 5%, we would consider that to be an unusual event. We'll see this idea pop up a lot as we get into some of the later lessons where we'll talk about significance tests. It's a way of trying to show evidence for or against a claim, and we'll use this benchmark of 5% as a way to determine whether or not the evidence is convincing or not. So, General Society surveyed 46,349 women. Asking how many women or how many children they had. The results are as follows. Okay, so we've got 0 to 7, and then just kind of clustered 8 or more into one group. And so using that cutoff of 0.05, that idea of 5% as separating unusual events, is it unusual for a woman to have 6 or more children? All right, so we are finding the probability. By the way, I didn't mention this earlier. I probably should have mentioned this. When we write this in shorthand, we just use P for probability, and then in parentheses, we just define the event that's desired. So in this case, the probability of having 6 or more children, I might just call X for children, and we want greater than or equal to 6. So in this case, we're looking at really these last 3 rows, and if we were to add those together, there are, in this study, 2,204 women who have 6 or more children. Out of the 46,349 who were sampled, and that gives us a probability of 0.048, which is less than 5%. So based on this sample, at least, we would say, yes, it is unusual. Having 6 or more children is unusual. All right. So that's just the idea of an unusual event. And like I said, it's just kind of a preview almost to some much more important uses that we'll have with that later in some future lessons. Okay. So Pepsi ran a contest for their 20-ounce bottles of soda. Some caps said free 20-ounce, while others said try again. Pepsi advertised 1 in 6 wins a free bottle. So I decide to take my statistics class to the store to see if this is actually true. Is 1 in 6 bottles really going to win? So I take 30 students, and each student buys a 20-ounce bottle, but only 2 students win, and the students are outraged, right? They're saying this contest is unfair. They're liars. They're just some big corporation trying to take our money. Because, of course, if we think about this, if 1 in 6 win, we would expect 5 winners, right? 30 students, we would expect if 1 in 6 wins, we'd expect 5 winners, but only 2 won, okay? So one of the things that we often do in statistics is we run simulations to try to recreate the situation. It wouldn't make sense necessarily to bring a bunch of people to the store or to just go by yourself and buy a bunch of these 20-ounce bottles, open them all up to see if you in fact win roughly 1 in 6 times. There's easier ways, there's more efficient ways, there's cheaper ways of simulating something like this to determine whether or not the contest is rigged or not, whether or not Pepsi is lying or not. Now, I would normally use Excel to do this. I'm not going to do that for this video, but the idea here is if I'm not going to use technology, for example, then I have to think about, well, what would work to simulate 1 in 6? In other words, what object or item or thing could I use to try to, that would represent 6 possible outcomes? So I could, for example, use a random number generator. I could just, there's a billion of them out on the internet. Just find a random number generator, ask it to generate random numbers between 1 and 6. Or I could use a 6-sided die, right? I could take a 6-sided die and I could roll it 6 times. So the idea here is when I make a simulation, I might take a 6-sided die, and we're going to get deeper into simulation in a future lesson, but this is kind of just a nice way to introduce the idea in the context of probability. I'm going to take a 6-sided die, I'll roll it 30 times. Now in this case, I'm wanting to know what is the actual probability, what are the chances that only 2 of these students out of 30 would have won if in fact you really do have a 1 in 6 chance of winning a Pepsi, winning this free 20-ounce bottle. So I might assign a 1 a 1 as win, right? And then a 2 to 6 as lose. So 1 in 6 wins, right? 1 out of the 6 possible outcomes on the die is a winner. The other 5 are losers. So I'm going to roll that dice 30 times, and then I'm going to count the number of ones. How many times out of 30 did I win? And if you think about this, I'll do this in terms of a dot plot, right? So you've got 0, 1, 2, 3, 4, and technically we need to take that all the way up to 30 because it's possible, though highly unlikely, that you would roll a 1 30 times. But the idea is you'd make a dot plot then, or you'd collect your data and you'd look at, okay, so maybe once we got 1 out of the 30, and maybe twice I got a 2, and then, got a bunch of 3s and 4s and so on and so forth, right, as we go through up to 30. What we're looking at then is because we're repeating this many times. We're going to do this many, many times. Like here, there's that idea again of repetition, right? We do this many, many times, and that's producing all of these dots because this number, this 1, the 2, the 3, the 4, is how many wins out of 30. Excuse me. So basically what happens here is I want to look at then, well, how many times did we get the results that the students had, which was 2 wins, or more extreme, in this case, or worse, 1 or 0 wins. So I might look at this and go, well, we were able to replicate that 3 times by chance using this die. Now, if I did this 30 times, let's say I did the simulation 30 times, that would be 3 out of 30, or 1 out of 10, or 0.1. Well, that's greater than 5%. So the conclusion I would come to is it's not rigged. They weren't lying. It's not unusual to get only 2 out of 30 wins when you've got a 1 in 6 probability of winning. So we can use simulation like that to see whether or not a claim is true. And this is what I was talking about earlier. We're going to do a lot more of as these lessons progress, is look at the claims being made and how do we use statistics, how do we use probability to determine where the evidence lies. Does the evidence lie for or against that claim being made? Okay, so let's move on then. So that's just a lot of what I would call basic concepts around probability. Let's get into the addition rule and the multiplication rule. And so talking specifically about situations where we have multiple events that we either want all of the events to occur or we want at least one of the events to occur. And how do we calculate and find those probabilities without necessarily having to make a probability model and do all of that work? So first of all, let's define what a compound event is. So a compound event, very simply, is the combination of two or more events. So in this case, there's two ways we're going to think about this. We're going to think about this as probability of A and B. And we're going to think about this in terms of probability of A or B. Another way to write this symbolically is instead of and or, kind of an upside down U is and a right side up U is or. Think union. Okay. So when we talk about or, by the way, I should mention this too. There's two ways to think about or, and this is kind of one way that I heard it. I really like this analogy. So when I go to Starbucks and I ask for a coffee, the barista asks, would you like sugar or cream? Now, when the barista asks that, they're not saying I can only have one or the other. They're saying I could have one or both of those things. I could have sugar, or I could have cream, or I could have sugar and cream. When I go to a restaurant and I order an entree, and the server asks, would you like soup or salad? That's different. They're not offering me both. They're saying you can either have soup or you can have salad, but not both. So in statistics and probability, when we talk about the word or, we're talking about the Starbucks. So think of Starbucks or here. So this could be A or B or both. Okay. All right. So mutually exclusive. Just some more definitions here to kind of make sure we've got the same language as we work through some of the examples and things like that. So mutually exclusive is the situation where two events are mutually, or I'll say it this way, two events are mutually exclusive. So two events are mutually exclusive if it is impossible for both events to occur simultaneously. And I guess maybe just so we don't pigeonhole ourselves too much, I'll just say that both events can't occur, okay? So for example, I flip a coin, the probability of a head and a tail, that's a mutually exclusive event. I can't flip a coin and get both a head and a tail in that event, okay? All right, then independent. And so watch these definitions carefully because it's very easy to get them mixed up. So mutually exclusive is exactly that. They are exclusive of each other. One cannot be with the other. They can't happen together. Independent says this. We're going to say that two events are independent. So two events are independent if one event does not affect the probability of the other. Does not affect the probability of the other. So take, for example, the flipping a coin and rolling a die. When I flip a coin and roll a die, and I'm looking at the combined outcome of those two things, a head and a 4, a tail and a 6, whatever it might be, those are independent events because the outcome of the coin, has no bearing on the outcome of the die. Likewise, the outcome of the die has no bearing or effect on the outcome of the coin. So probability of a head and a 6 would be independent events for that reason. All right, so they can both happen when they're independent, but one doesn't affect the other. So that's kind of the difference. Mutually exclusive, they just simply cannot happen together. They cannot coexist, so to speak. Okay, complement. So when we talk about a complement, we're saying that the complement of event A is the event that does not occur. So that does not occur. It's a little bit of a goofy way to define this maybe, but basically what this is saying is if I say that A is some event, its complement is basically saying that A didn't happen. It's kind of the opposite of A, or anything that couldn't be A. So again, if I think about rolling a die and I assign the event A to rolling a 1, the complement is rolling a 2 through 6. If I flip a coin and I assign A to getting heads, the complement is getting tails. Okay, so it's whatever it can't be. And when we talk about complements, we're going to denote it with A superscript C. Okay, so the event A, the C, just telling us that it's the complement of A. When we talk about it in terms of probability, then if I want to find the probability of a complement, thinking about the fact that a complement is basically what A isn't. If you were to combine A and A complement, you get the entire sample space. Okay, so let me do this off to the side here. So if I say that A is getting a 1, and I'm rolling a 6-sided die, A complement is getting a 2 through 6. Well, together, those two things make up all the possible outcomes of rolling a 6-sided die. So there's 100% probability of getting A or A complement, of getting one of those two outcomes. So if I think about that in mathematically, then I'm really saying that A plus A complement is equal to 1, is equal to 100%. So when we think about finding the probability of the complement, if I just rearrange that a little bit, the complement is just 1 minus A. Or obviously you could rewrite it and say the probability of A is 1 minus the complement. Okay? Where this is very, very helpful is in an OR situation, kind of like I just described here with the dice. So if I wanted to find the probability, for example, of getting a 1 or higher, or excuse me, maybe I should say a 2 or higher because there's no 0, of getting a 2 or higher, I could find the probability of getting a 2, probability of getting a 3, a 4, a 5, and a 6, and add them all together. Not real difficult with a small sample size like that, or a small event size like that. But if I was dealing with something much larger, or something that's much more complicated to find the probability of, it would be easier, rather than trying to find the individual probability of 2, 3, 4, 5, and 6 and adding those together, I would instead find the probability of 1 and then just subtract it from 1. Because if I find 1 and subtract from 1, that gives me everything else, 2 through 6. And we'll see an example of that in just a little bit. Okay, last thing before we get into some more examples here, and that is the general addition rule. And this deals with the OR situation. So whenever you see OR in probability, just think addition. I want this or this or this. I find the probability of each and I add them together. So the probability of A or B is the probability of A plus the probability of B. Now, this would be true if they were mutually exclusive. So this part is true if mutually exclusive. But if they're not mutually exclusive, it means that A and B can happen at the same time. And what's going to happen is if I count all the ways I can get A and find that probability, count all the ways I can get B, get that probability, and add them together, there's a chance that I have double counted one of those things. And so what I need to do is, when it's not mutually exclusive, I need to subtract the probability of A and B. I need to kind of subtract the overlap of those two things happening together. So this is only necessary when those events are not mutually exclusive. Not mutually exclusive. Okay. So let's go ahead and get into some examples and start to work with some of these concepts that we just talked about then. So a Pizza Plaza served 60 customers for lunch. 52 ordered pizza and 16 ordered salad. 12 of these ordered both pizza and salad. Okay, so think kind of the idea, and we're going to make a Venn diagram here, but think Venn diagram. Think of this idea that you've got a group of people. It says make a two-way table and a Venn diagram. I'm going to start with, actually start with the two-way table. I actually think that's easier than a Venn diagram. So think of the fact that you've got people who ordered pizza and people who didn't. And statistically, from a probability perspective, we're going to call that PC, right? That it's the complement. So if people ordered pizza, that's P. If they didn't order pizza, they're the complement. They're PC. Okay, and then the same with salad. They either ordered a salad or they didn't order a salad. All right, so we get this table then because some of those people did both and some of them did neither. So in this case, I'm going to actually extend this table a bit. We're going to make some totals here just to see how this all works out. So we know that there's a total of 60, right? So that number right there has to be 60. The total of the table is 60. 52 ordered pizza and 16 ordered salad. 12 of these ordered both. So the cross-section of pizza and salad is 12. If 52 total people ordered pizza, this total column has to be 52. If 12 did both, that leaves 40 who ordered pizza only, but not salad. 12 plus 40 is 52. Likewise, 16 people ordered salad in total. Now, some of them may have ordered pizza, some of them may have not, but 16 people ordered a salad. So again, if 12 of those people ordered a pizza, that leaves 4 people who didn't order anything. Now remember that the total of this table has to be 60. So right now we've got 12 people who ordered both, 4 who ordered salad but no pizza, and 40 who ordered pizza but no salad. If we add those together, we are at 56 total people, which means 4 people didn't order salad or pizza. They got the wings or whatever. So 44 people did not order salad in total, and 8 people did not order pizza in total. So that's what a two-way table would look like, and that's how you want to approach it and create it when you're given that information. Just plug in what you know, and then just start to kind of logically work backward to figure out how those other boxes fill in. Likewise, we could do this for a Venn diagram. And so in this case, a lot of people don't put boxes around their circles. We really want a box because that box represents everybody. So again, in everything that I put into this box, I want a total of 60. One circle specifically represents pizza. The other circle represents salad. The outside of those circles, so kind of that space between the circles in the box, that's going to be the people who didn't do either. Now again, in a Venn diagram, we could set it up the same way we did the table. We know that there's going to be a total of 60 when we count up all the numbers in this Venn diagram. That's our goal. 12 people ordered both salad and pizza. That 12 is the intersection of those two circles. We know that 52 people ordered a pizza, so 12 are already accounted for, so we need another 40 people to give us a total of 52 in this circle who ordered pizza. And then likewise, we have 16 who ordered a salad. And so if 12 are already counted, we have 4 remaining to fill in this circle for a total of 16. Now again, if you count up what you have, you've got 56 people who ordered one of those two things or both. leaving 4 people who didn't order either. So same values, you'll notice that those are the same values that we have over in the table in these 4 main squares. And you can kind of see how they line up and match with each other. Okay, so now that we have that, let's go ahead and find some probabilities. It says find the probability that a randomly chosen customer ordered a salad. All right, so if we look at either one of these, the table might be a little bit easier to look at. Basically, I'm just looking at that entire row for salad. 16 people out of the 60 ordered a salad. Now you can reduce that, you can put it into a decimal. I'm just going to leave it for the purpose of this activity. Ordered pizza, so again, now we're looking at all the people who just simply ordered a pizza, whether they ordered a salad or not, we don't really care. And so we're looking at that first column, 52 out of 60 people ordered a pizza. And then ordered a pizza or a salad. Okay, so this is where this idea of the general addition rule comes into play, right? We're dealing with this or, so pizza or salad. So I want the probability of pizza plus the probability of salad. Now in this case, these are not mutually exclusive, right? They can both happen at the same time. Don't get this confused with independent. They're independent, or at least we're going to assume so, that whether or not a person orders pizza doesn't have an effect on whether or not they order a salad. They're just going to either do one or both or neither. But in this case, they are not mutually exclusive, so we need to subtract the probability of both of them happening at the same time. So the probability of ordering a pizza, we just figured out, was 52 out of 60. The probability of ordering a salad is 16 out of 60. And you'll notice right away that that doesn't make sense if we stop there, because we'd have 68 over 60, and that's over 100%. We can't have more than 100% of people doing something. So that right there should kind of be a red flag that we need to do more to this. And we're going to subtract the probability that a person did both pizza and salad, which is 12 out of 60. So when we do that, we get 56 out of 60. Think about what's happening up in this two-way table. Now, I'm going to show this 2 different ways. First of all, when we think about finding the probability of ordering pizza or salad, again, or is one or the other or both. So one ordered just salad, or just pizza, or both. If you just add those 3 numbers together, that gives you the 56 people out of 60 who did pizza or salad. The other way to think about this, when we think about this in terms of the formula, probability of A plus probability of B minus the probability of both. The probability of A, we said, was pizza. So we're looking at all of these people right here. In fact, let me kind of clean this up a little bit. We're looking at all of these people right here, 52 people. The probability of salad is all of these people right here, 12 and 4 or 16. But notice what happened as I was circling those. I ended up circling the number 12 twice. I counted it twice. I double counted those people, and that is why we need to subtract the 12 people that we double counted. Okay? All right. So the other way, just to bring in the complement idea, let's just talk about one more way here. I could do 1 minus the complement of this situation. So the complement would be that they didn't order either, right? They either ordered a pizza or a salad or both. The complement is that they didn't order a pizza and they didn't order a salad. Well, that's 4 people, right? 4 people did not order a pizza and a salad, right? Those 4 people. And so 1 minus 4 out of 60 is 56 out of 60. So there's a variety of ways you can do this depending on what pre-work you've done in terms of maybe creating a table or a Venn diagram. Mathematically, you can kind of take a direct approach. You can do a kind of an indirect approach with complement. And so it just oftentimes is dictated by the problem, by your comfort level, just how you see the problem. But just understand that there's not always just one way to do some of these problems. All right, so we're going to get into conditional probability now. And in conditional probability, again, this is finding the probability of something happening given or conditioned by something else also happening. So when we talk about conditional, the notation for this is if we're going to talk about B conditioned on A or given A, we're going to write it like this. So you just kind of put a bar between the two ideas. And so this is literally just read the probability of B given A. So that little bar, you can just kind of think of that as the word given or conditioned. Mathematically, the way that we find this is we find the probability of A and B, and we divide that by the probability of A. All right. If all outcomes, so if all the outcomes are equally likely, then we can say that the probability of B given A, let's try that again, probability of B given A is the number of outcomes for A and B. So this kind of goes back to that kind of traditional thinking about how we might find probability. Probability of outcomes for A and B divided by the number of outcomes for A. All right. So we're introducing now this idea of and. We've talked a lot about or, addition. So because we're introducing and, let's talk about and. How do we deal with and? And that gives us the general multiplication rule. So when you see the word and, think multiplication, or addition and multiplication. So the probability of A and B is the probability of A. Now, I'm going to write the more broad equation. I'm going to give you a simpler equation for some circumstances. It's the probability of A times the probability of B given that A occurred. This is in the situation where those two events are not independent, where one is going to impact the other. So again, if I'm looking at A and B, A happens and then B happens. If A impacts B, then I have to take that into account because B is going to have a different probability now because of A. So that's the conditional part. We could write this as probability of A times probability of B without having to worry about conditions if they're independent. So if one doesn't impact the other, then we just go ahead and just do it this way. Let's go back to our dice example just for a minute before we get into the actual examples that we're going to go through for this. When I roll a die and flip a coin, the coin has a 1/2 probability, right? Half probability of heads, half probability of tails. The die has a 1 in 6 probability. So if I think about the probability of heads and 6, in fact, let me write that with and, so we're real clear on this. Heads and 6. Well, this is saying take the probability of, because they're independent, right? What the coin does has no impact on the die. And so if I take the probability of heads times the probability of a 6, that's going to be 1/2 times 1/6, which is 1/12. And if you remember back to our sample space, or excuse me, our probability model, we said that all the probabilities of those outcomes were 1 in 12. Okay? All right, let's take a look at some examples here. So it's a company, we're going to look at one where it's not independent, so where we have that condition. We're going to look at one where they are independent. In fact, it's similar to what I just did, actually. And then we'll do kind of a little bit of a larger problem, so to speak. So a company interviews 1 in every 10 people who apply for a job. Of those interviewed, 1 in 4 are hired. What is the probability of an applicant getting a job? So we want to know really what is the probability that you get an interview and you get hired. Well, in this case, they are not independent, right? Because whether or not you get an interview impacts, obviously, whether or not you get hired. And so that probability changes. And so we have to look at the probability of being interviewed times the probability of getting hired given that you got the interview in the first place. Well, these values are already given to us in that way. Notice that it says the probability of being interviewed is 1 in 10, or 0.1. The probability of getting hired is 1 in 4, right? It says if you are interviewed, of those interviewed, you have a 1 in 4 chance of being hired. So they're already giving us that 1/4 or 0.25 as the conditional value or the conditioned value. So in this case, you would have overall, if you apply for the job, you have about a 2.5% probability or 0.025 probability of being hired. Okay, this is the problem I actually just did. We'll go through it again real quickly here, but so it says a coin is flipped and a six-sided die is rolled. Find the probability of getting a head and rolling a 4. So again, probability of a head and a 4. Well, 1/2 probability of a head. In fact, let me write this out again just to have this. Probability of head times probability of a 4, again, independent, so we don't have to worry about conditions, is 1/2 times 1/6, which is 1/12. Okay. All right. Let's do one more problem of probability here, and then we're going to get into just some counting principles. So this is a situation where we're going to play a game with 3 aces and 2 kings. We've got basically 5 cards. And the player draws 2 cards without replacement and wins if they get a pair. So they draw a card, it's an ace, they set it aside. They draw another card, if that's also an ace, they win. Same thing would happen if they drew the 2 kings. Find the probability of each. Okay, so if you think about what's happening here, if I want to draw 2 aces, obviously there's conditions here because we're not replacing. I draw a first card, that impacts the probability for the second card. So if I'm looking to win on 2 aces, then I would have a probability of getting a 3/5 probability of drawing an ace the first time. There's 3 aces out of 5 cards. But now assuming that I drew an ace, there's 1 less ace in the deck, so now there's only 2 aces, and there's only 4 cards total. So when you do this, you've got to think in those terms. You have to think about, after I draw that first card, what's left, and therefore what's the probability of that for that second card. So in this case, then we have a 6 out of 20 or a 30% chance, 0.3. All right, 2 kings, similar idea. There are 2 out of 5 to begin with, but again, assuming then that the first card is a king, there's only 1 left out of the 4 cards remaining. So there's a 2 out of 20 chance of getting a king, which would be 0.1. So at this point, I guess I'll stop here. I'm going to stop here because the next one is probability of winning, right? So what is the probability of winning? Well, the probability of winning is the same as probability of 2 aces or 2 kings, which is the probability of 2 aces plus the probability of 2 kings. Well, we just found that. Probability of 2 aces was 0.3. Probability of 2 kings is 0.1. So you have a 40% chance of winning this game. Okay? All right, so now some conditionals. Probability of winning given that the first card was a king. Okay? Well, that really means then that you're winning on 2 kings. So when we think about the probability here, we're really saying that the probability of A and B, right, divided by the probability of A, where A is winning, or excuse me, A is king. Okay, so then let's take a look at the probability of winning given that the first card was a king. So again, thinking about our formula here, probability when we have a conditional like this is the probability of A and B, we need a second A there, A and B divided by the probability of A. In this case, B is winning. A is that the first card was a king. Okay? So the probability of A and B of winning and doing it on kings, right? Because if your first card is a king, your second card has to be a king. Well, again, that we found in part B. There's a 10% chance of that happening. The probability that the first card is a king, well, we found that also in B, right? We found that right here, we found that the probability was 2 out of 5. And so your denominator is 2 out of 5, or 0.4. So in this case, we have a 0.25 probability, or a 25% probability of winning, given that you draw a king on the first card. All right, and then the probability of the first ace, that the first card is an ace and losing. So again, I'm going to call this A, I'm going to call this B. And so the probability of both of them, drawing a card and losing. Okay, well, let's think about that for a minute. We know that the probability of both of them happening together is 0.3. Why do we know that? All right, let's take a look at an example that involves playing a game with 5 cards. 3 of them are aces, 2 of them are kings. And the way the game works is you draw a card, you set it aside, you draw another card, and if those 2 cards match, in other words, if they're both kings or both aces, you win. And so we're going to find the probability of various outcomes here. And so in the first case, we're going to find the probability of 2 aces. So we obviously have a situation where they're not independent, right? When you draw a card, you're setting it aside. That changes the probability of that second draw. So the probability of 2 aces is really getting the ace and another ace. So if I think about it this way, I've got a 3 in 5 chance or probability of drawing an ace on the first draw. There's 3 aces in the deck. There's 5 cards total. Assuming that I've already drawn an ace then on that first time, there are only 2 aces left in the deck out of 4 total cards. And because this is an and situation, I want an ace and an ace, I'm going to simply multiply those 2 things together. And I have a 6 out of 20 probability of winning with 2 aces, or 0.3. Okay, 2 kings. If I have 2 kings, then again, the first draw, there's 2 possible outcomes out of the 5. Assuming that I've now drawn a king, there's 1 king remaining out of 4 cards. And so the probability is 2 out of 20, or 10%. All right, probability of winning. Well, that's just really asking what is the probability then of getting 2 aces or 2 kings. Well, we just found that, right? And because it's or, we're adding, so the probability of 2 aces is 0.3. The probability of 2 kings is 0.1. So our probability is 0.4, or 40%. So you've got a 40% chance of winning this game that we're playing here. All right, let's do a couple of conditional problems here. So find the probability of winning given that the first card is a king. Okay, so I'm going to call this B, right? B given A. And we want to find the probability of A and B divided by the probability of A, the condition part at the end. So we already know that the probability of getting a king and winning, both of those happening, would only happen if you draw 2 kings. Well, we know that the probability of drawing 2 kings is 0.1. We just found that in part B. The probability that the first card is a king, we also have in part B, because when we found this 2/5, that was the probability that the first card was a king, 2 out of 5. So we're going to divide by 2/5, which as a decimal is 0.4, right? This is 2/5. and that's going to give us a probability then of 0.25. So we've got a 25% chance of winning, given that the first card was a king. So the last one is finding the probability of the first card being an ace, given that we lost. So again, if I think of first card ace as B and losing as A, the probability of drawing a card, an ace, and losing, we actually find in part A, it's actually the same probability, because if you think about what it would mean to draw an ace and lose, drawing an ace has a 3/5 probability on the first draw. In order to lose, that second card would have to be a king. Well, there's 2 kings left out of the 4 cards remaining, which is exactly what we did in part A when we found 2 aces. So those probabilities are the same. So there's a 30% chance of A and B. So that's going to be our numerator. And then the probability of losing, well, we know that the probability of winning is 40%, which means that the probability of losing has to be 60%. And so there is a 50% probability that you would draw an ace first and lose the game. Okay? Now, that's kind of tricky. Some of those problems might be a little bit tricky, might be causing your head to hurt a little bit, and that's okay. Let me talk about a way to organize this that would help to kind of visually and mathematically see what's going on, and that's to use what's called a tree diagram. So a tree diagram is where we literally map out in using branches. Almost think of like a genealogy tree where you have like a mother and father, and that branches out to children, that branches out to grandchildren. It's kind of a similar structure here. What we're going to do is we're going to start with that first card. And when we draw the first card, there's 2 possible things that can happen. So we're going to draw 2 branches. I draw that first card. It could be an ace, or it could be a king. Now, because there's 5 cards, 3 of them are aces, 2 of them are kings, we know that there's a 3/5 probability that it would be an ace, and it's a 2/5 probability that it would be a king. So now I have to draw a second card, and we know that that second card also has 2 possible outcomes. It could be another ace or a king. Or down here, it could be an ace or a king. Now again, when we think about the probability of the second situation, we want to include the outcome of the first situation, the first event. So when I'm looking at a second ace, I would say that there's 2 aces left out of 4 cards. There's 2 kings out of 4 cards. And then same below for the king, all 3 aces would be left out of 4, and there would be 1 king left out of 4. Now notice something as we're creating this tree. If you look at the first 2 branches, the 3/5 and the 2/5, so I'm looking at kind of that column, if you will. 3/5 plus 2/5 adds up to 1 because it accounts for every possible outcome in that first draw. And if I look at that second column, don't total up the whole column, but just total up each part. So if I draw an ace, after that I have to either draw an ace or a king. So that kind of represents 100% of what can happen there, 2/4 plus 2/4. And then same down below for the king. If I look at that as kind of a subset, I would either get a king and an ace or a king and a king. That's 100% of the outcomes after a king. Okay. Now here's what happens. This represents all 4 possible outcomes of this game. And because I want a card and a card, I'm going to simply multiply those probabilities together. So the first one is the probability of an ace followed by an ace, which is just 3/5 times 2/4, or 6/20, which is 0.3. The second situation is an ace followed by a king. That has a 3/5 and a 2/4, which is also 6 out of 20, or 0.3. The third situation is a king followed by an ace. That's a 2/5 times a 3/4, which is also 6 out of 20. Hopefully the last one is not the same, or we're in trouble, because that's going to be bigger than 1. And then we've got a king and a king, which is 2/5 times 1/4, which is 2/20, or 0.1. And again, here now, because this last column is every possible outcome and their probabilities, this is basically our probability model now, that should add up to 1. 0.3 plus 0.3 plus 0.3 plus 1, 0.1, because that's all of our possibilities for this situation. So now when I think about answering these questions, what is the probability of drawing two aces? Well, two aces is this very first row, right? It's an ace followed by an ace. If I look at the second question, the probability of two kings, that's the very bottom row. Probability of two kings is 0.1. The probability of winning, well, again, it's just those two things added together, the 0.3 and the 0.1. But now look at what happens with the conditionals. And this is where it's not, we're not going to see it directly, but we can kind of start to see the numbers a little bit easier here. Probability of winning, given that the first card is a king. So where the first card is a king, we're kind of looking at this bottom half, right? So that first card is a king. And we want the situation where we win, given that that happens. Well, winning in that bottom half is a 0.1, and then divided by the probability that the first card is a king. Well, in this case, then we have to go back to then that 2/5. We have that 0.1 and that 0.4. So the tree diagram, it's not a perfect model. It's not going to just shout out all the answers to you, but it does help to organize and start to see where these numbers are coming from, and might make some of that math just a little bit easier. Okay. So let's finish up our probability with this, and then we still do have some counting principles to look at. So it says Mark flips a coin 5 times. Find the probability that he gets at least two heads. Okay, so our event is at least two heads, and this is what I was talking about earlier now with the complement. Because if I want to find the probability here, it really means 2 or 3 or 4 or 5, because he's flipping this coin 5 times. So I would have to find those 4 probabilities and add them all together. The complement, however, is 0 or 1 head. In other words, less than 2 heads. And so now, instead of having to find 4 probabilities, I can find this by just doing 1 minus 0 or 1. Okay? So think about that complement in situations where you're having to find a lot of probabilities because you're kind of doing it like an at least or maybe a less than, where you're having to do more going the one direction than you would if you went the other direction. So in this case, if I want to find the probability of at least 2 heads, I'm going to kind of write this out formally. I'm really then finding 1 minus the probability of 0 or 1 head. Notice here that we're going to find that whole probability first and then subtract from 1, okay? So OR is add. So if we want to even break this down further, it's really saying find the probability of, or 1 minus the probability of 0 heads plus the probability of 1 head. Okay. All right, so let's think about this. If I want to get 0 heads, that means that when I flip a coin, well, actually, let me back it up even further than that. When I flip a coin, there's 2 outcomes, right? And we're going to flip that coin 5 times. So I would have 2 outcomes for the first and 2 outcomes for the second and third and fourth and fifth, or just simply 2 to the 5th, or 32 total possible outcomes. So think of that as our denominator, okay? So now when I think about the probability of 0 heads, well, there's only one way to get no heads out of 5, right? There's just, you're going to get no heads. So the probability of no heads is 1 out of 32. The probability of 1 head is getting a head on the first or the second or the third or the fourth or the 5th flip. So there's 5 different ways that you can get 1 head out of 5 flips. Now, Think about having to do this the other way. If we had done the probability of 2, 3, 4, or 5, you would have to figure out how many ways can you get 2 heads, how many ways can you get 3 heads, how many ways can you get 4 heads. 5 is obviously just 1. That would be a lot of work. Okay, so this is a much, much easier way. So our probability then of at least 2 is 1 minus the 1 over 32 plus 5 over 32, which is going to be 26 over 32, or 0.8125. So I just wanted to give you an example, kind of a concrete example of how you can use a complement to make a problem much more efficient than trying to hit it kind of straight on. Okay, so that's everything with strictly probability. Let's move ahead now and let's talk about counting principles. And thankfully, this is not a real long section. This is a long video, and I'm getting a little tired myself. You can see that in some of the mistakes I'm making. But for counting principles, we really just want to talk about how do we count the number of ways something can happen. Because as you've seen, being able to find the number of desired outcomes or the number of possible outcomes for our numerator, our denominator, things like that, is a pretty important thing. So fundamental principle of counting just simply says that the number of ways several operations can be performed is equal to the product of the number of ways each operation can be performed. Okay, so this is a really long-winded way of saying if you want to know, if you've got several events and you want to know how many ways can those events happen, you're just going to multiply how many ways each event can happen. Okay, so if I want to, I'll just give you some examples here. If I want to, again, we'll just keep on flipping coins and rolling dice because why not? If I want to flip a coin and roll a die, there's 2 ways to flip a coin. There's 6 ways to outcomes on a die. That's going to give us 12 outcomes. Okay. If 8 people are competing for gold, silver, and bronze. We just had the Olympics recently at the time of this recording, and so appropriate to talk about gold, silver, and bronze here. We would have 8 people possible for gold, right? Any one of those 8 could win the gold. Now, again, the idea here is that if one wins the gold, they're out of contention for the silver or bronze. So there's 7 people left who could win the silver. There's 6 people who could win the bronze. We just multiply those all together. There's 336 different possible outcomes of awarding the gold, silver, and bronze to these 8 competitors. Last one that I'll give you on this one is, let's say we want to seat 4 children in a row. So again, you've got these 4 seats that you're trying to fill. You've got 4 children to choose from for the first one, 3 for the second, 2 and 1. We just simply multiply those together, and that is 24. This is probably a good time also to talk about factorial. If you don't know factorial, when you multiply all of the whole numbers from a value down to 1, you are basically taking what's called factorial. And so factorial, 4 factorial is 4 times 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7 all the way down to 1. Okay? And so some of your calculators may have an exclamation button. You may have to go into a menu to find it, but you can do factorial on many calculators. If you're in something like Excel, I believe the function is just like FACT. If you just start typing in factorial, something will pop up that'll be obvious. Okay, So that's pretty simple then, where you're just multiplying kind of all the ways. Like another simple example is, let's say, it's kind of the classic example of you've got 4 shirts and 3 pairs of pants and 2 pairs of shoes in your closet. So you just, how many different ways can you dress yourself, at random? You just multiply the 4 different shirts times the 3 different pairs of pants times the 2 different shoes, and that's going to tell you how many different ways you can dress yourself at random. Permutations and combinations. This is a fairly common one also that we see when we're doing kind of, especially like what I would call academic probability. A permutation is just simply a way of counting the number of events that could occur, how many ways an event could occur, when you've got a couple of conditions in place. This is, first of all, where you are choosing R items from N items. So you've got, you're choosing 3 people from a group of 8 people, or you're choosing, whatever the case may be. So R from N. And permutations specifically, what's important here is the fact that order matters. So back when I talked about the 8 competitors for a gold, silver, and a bronze, if Julie gets the gold, that's different than if Julie gets the bronze, right? The order matters. She's certainly going to care whether or not she got the gold or the bronze or took 4th or 8th. So order matters in how we place those people. So that's a permutation. The way that we write permutation, there's different ways to write it. You might see it written like this. Typically, where you've got kind of this NPR. N, again, is the total number of items. R is the number that you're selecting. And the way that we find a permutation mathematically is we just take the number of items available times n minus 1 times n minus 2, and we keep doing that until we get to n minus r plus 1. Okay, so think about our 8 competitors, okay? For our 8 competitors, we took 8 times 7 times 6. We took 8, that was n, right? 8 people to choose from. Subtracted 1 times 7, subtracted 1 more times 6. If you take 8 minus 3, because we were technically choosing 3 people here, 8 minus 3 is 5, plus 1 is 6, so we stopped at 6. All right. Now, obviously, we know to stop at 6 because we knew we wanted to basically fill 3 slots, and that would be the other way to think about it. There is a formula, so you don't have to keep multiplying 8 times 7 times 6 times 5 and so on and so forth, and that is to take n factorial divided by n minus r factorial. Okay, so if you've got a calculator or use some kind of technology online or something like that, Excel, you could do factorial to simplify the process just a little bit for yourself. All right, so I'm gonna do that example of 8 choosing 3 that I just did with the gold, silver, bronze. So 8 people choosing 3. We've got the three places. So in this case, we've got 8p3, which if I use the factorial is 8 factorial divided by 8 minus 3 factorial. Oops, put that exclamation on the outside. Okay. Now, what we have then, if we simplify this down, we get 8 factorial divided by 5 factorial. Think again about what factorial means. Factorial means you are multiplying 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial, similar idea, 5 times 4 times 3 times 2 times 1. Because we are multiplying in a fraction, we can cross things off in the top and the bottom that are the same. So we have this entire string, 5 down to 1, in the top and the bottom. That entire string crosses off, and notice what you have left is 8 times 7 times 6, or 336. Okay? So that's how you can kind of do that. If you don't have factorial capability, you can do it that way. I also do want to mention, if you do want to use Excel, even beyond factorial, if you want to do a permutation on Excel, so if you want to just do 8 choose 3, the function name is permute. They just cut it off at that first T. So PERMUT. So equals, you just type in equals permute. and then in parentheses n comma r. So if you did, in this example, if you did equals permute 8 comma 3, it is going to give you the answer of 336. So I'd certainly encourage you to use technology and not trying to do a lot of this by hand. All right, so let's talk about combinations. So permutations, again, you've got a group, and from that group you're drawing a certain number where order matters, okay? In a combination, the same idea applies. We're going to choose R items from N items. But in this case, the difference is that order does not matter. So if you think about like the days of your high school locker, and we called that little dial on the locker, if you had one of those lockers in high school, we called that a combination lock, because we thought, we could have thought of it as a combination of numbers, but that's not really a combination locker, is it? It's actually a permutation locker, because the order in which you put in those numbers mattered, okay? When a true combination order does not matter, we're simply concerned about the combinations that we can select, or the groups that we can select, not in the order that those groups are selected. Similarly, you might see notation like this, NCR. And in this case, the formula is n factorial divided by n minus r factorial, so exactly the same as permutations, except that we are also going to divide by r factorial. That's the only difference in the formulas, is that we have an r factorial in the denominator. I'm going to talk in just a little bit why that is. But let's go ahead and let's just do an example here. So let's just suppose that we select 3 people from 8, just like we did before. Okay, but this time just to serve on a committee. So no titles to serve on committee. So no titles, doesn't matter. They're just 3 people serving on a committee. So this would be a combination, and we are going to take 8 factorial divided by 5 factorial, just like we did for the permutation, except we are also going to multiply by that 3 factorial. Okay, so if we do that, I'm just going to jump right to the chase here. We get 56 unique committees. John and then Julie are selected. Julie then John are selected. It doesn't matter. They're both on the committee. So where is that 3 factorial coming from? Well, let's suppose that we have 3 people. We'll just say Ann, Bob, and Chuck. All right, so Ann, Bob, and Chuck are going to serve on our committee. And again, it does not matter what order they were chosen. So they could have been chosen A, B, C. They could have been chosen A, C, B. They could have been chosen BAC, BCA, CAB, or CBA, right? So there are 6 different ways that they could have been chosen. All 6 of those, in the eyes of the problem, are the same. They're still the same committee. Well, 3 factorial is 3 times 2 times 1, which is 6. So that 3 factorial, what we're doing is we're dividing by the number of ways that something can happen where the order was just simply changed, to get rid of all of those repetitions, right? So when I divide by 6, 6 divided by 6 is 1. These 6 divided by 6 become counted as 1. That's why we divide by that n factorial, okay? All right, so let's do one more example here. I'm going to finish up with one last example. We're just going to write this out here. Let's suppose that a crate contains 100 springs, and it is assumed, we're going to kind of look here at how do we kind of use these ideas with probability. We're going to assume that 3% are defective. So 3 of the 100 springs are not good. They're fragile, they've got a weak spot, whatever the case may be. 10 springs are selected at random for inspection. All right. And what we want to know is, we want to find the probability that all 10 are not defective. Okay, so we're going to find the probability that all 10 are not defective. Okay, so first of all, we need to figure out how many ways you can choose 10 springs out of the 100, right? So the total ways to choose 10, think about whether or not order matters here. And it does not, right? If I choose 2 springs, I don't care what order they came out of the crate, I have those 2 springs. So this is a combination, so we've got 100 springs, choosing 10 of them. So again, 100. By the way, I should mention too, and I'll just write it right up here. In Excel, if you want to do a combination, I'm going to write this out, but if you want to do this in something like Excel, it is equals combin n comma r. Okay, so you've got that option also to do this. Again, some of you might know how to do this on your calculators. If you want to do this with the factorial, it's 100 factorial divided by 10 factorial times 90 factorial. And in this case, I'm gonna leave it like this for now, and there's a reason why. I'm gonna show you how this does kind of work out nicely mathematically. You could certainly just figure out what that number is and keep going. Now we need the ways to select 10 good, right? Because we want the probability that none are defective. Another way of saying that none are defective, all are good, right? So there are 97 that are good, and we want to choose 10 of them. So similarly, we are going to take 97 factorial divided by 10 factorial times 87 factorial. Okay? All right, so basically what we have now is the numerator and denominator for our probability. The probability that none are defective is the 10 ways of getting 10 that are all good, 97 factorial, divided by 10 factorial, 87 factorial. Now, you might be wondering, why are you doing this? Why don't you just use Excel? Why don't you just use your calculator and get the number? I just want to show you kind of, in this kind of a situation, it may not be necessary to do that. It's actually almost easier or faster to do this, because when I divide that by the 100 factorial, divided by 10 factorial, 90 factorial. Notice what happens here. If dividing by a fraction is the same as multiplying by its reciprocal. So I'd have 10 factorial times 87. I'm sorry, I just lost my place here. Lost my train of thoughts. Okay, and what's going to happen here is whoops, I forgot to flip that fraction. Sorry about that. Flipping the fraction, 10 factorial, 90 factorial over 100 factorial. Okay, so what's going to happen here is those 10s are going to cancel when we multiply. And in essence, the 97 over 100, well, 97 down to 1 is going to cancel the 97 down to 1 in the 100. So you'd literally have 100, times 99 times 98 on the bottom. And similarly, the 90 factorial over 87 factorial, the 87 factorial cancels 87 down to 1. So you'd have 90 times 89 times 88. Okay, so that whole complex formula stuff, in this case, just boils down to multiplying 3 numbers together in the numerator and the denominator and dividing. Again, just to show you that mathematically sometimes these do simplify very nicely. In either case, we get a probability of 72.7% or 0.727. Now, why might we be curious to do a problem like this? If I know that just by the nature of the process, that when I'm producing springs at my factory, that some of those springs are going to be defective, and I want to do a quality control to just kind of ensure that what I'm shipping out to my customer is good, that we're not exceeding certain, limits on quality, things like that, that we're not, sending out boxes that are just full of defective springs and things like that. If I send out 100 springs and I know that there's a good chance that 3 of them are defective, I want to maybe take a large enough sample to make sure that I'm at least catching one of those. Okay. So in this case, what we find then is that when we sample 10 springs out of the 100 and 3 are defective, there's a roughly 73%, almost 3 out of 4 chance that all 10 of those springs are going to be good. Now part of that is great, right? I mean, it's great that we're taking a sample and they're all good. It's telling me that in general, those springs are probably good. Because if more were defective, I would expect to find more defective springs, or that the chance of getting no defect would be much lower. So that's positive. The negative is that 10 might be too small of a sample size, because if there's a roughly 3 and 4 chance that I'm not going to find any defective springs, then it starts to kind of beg the question, well, then what is the point of sampling if I'm not going to find any defective springs anyway? Okay, so it's just an example to show how we can kind of combine also then the idea of a combination or a permutation into finding a probability. All right, well, that was a very, very long lesson, and I thank you for sticking it out with me, and I certainly look forward to seeing you in the next lesson. Take care.